What if I told you that without load balancers, your favorite apps would crash under pressure? Netflix, Instagram, WhatsApp, they serve millions or even billions of users every day. To keep those apps running smoothly without crashing, they rely on some pretty clever engineering tricks. One of the most important being load balancers. Hello world, my name is Monis and today we are diving into the world of load balancing. By the end of this video, you will get a clear picture of what exactly is a load balancer and how it keeps your servers from becoming a traffic jam. And then we will also discuss the different load balancing algorithms and how they decide which server gets which request. So without further ado, let's get started and master the art of balancing server loads. Imagine that you're at a bank and you would like to deposit some cash in your account. The moment you enter the bank, you see 3 counters for serving the customers. Each counter has multiple responsibilities like ability to open a new account, close an existing account, deposit cash, and such. Now, each of these activities can take a different amount of time. For example, we know that depositing money into the account would be much faster than opening a new account. Obviously, you want to quickly deposit the money and go home. But if you have to pick a counter yourself, you don't know how much workload each counter has. However, if there was an employee whose sole job is to do 2 things, that is, keep a track of workload on each counter and to direct customers to the right counter by using this information. This will ensure that the workload among the employees is evenly distributed and the customers are also served quickly. This is the basic fundamental of a load balancer. Thinking about this example in the world of software engineering, in modern applications which are large scale and have millions of active users, we often have multiple servers which are replicas of each other, and each replica hosts exactly the same functionality. So when these millions of users interact with the application, their requests go to one of these servers. A load balancer is a hardware or a software which distributes these requests evenly to the underlying servers, and it does so using an algorithm. There are many load balancing algorithms, but they are broadly divided into 2 categories, namely static and dynamic. Dynamic load balancing algorithms keep a track of the latest state of the servers and use this information to decide where to send the next incoming request. However, static load balancing algorithms don't take this information into account. So let's discover both of these categories in a bit more detail, starting with static load balancing. The first and the most common static load balancing algorithm is the round-robin algorithm. If there are 3 servers A, B, and C, then the load balancer will send the first request to A, the second request to B, and the third request to server C. Once it receives the 4th request, it starts again from server A and repeats this process. Another variant of this algorithm is the weighted round-robin algorithm. This algorithm is particularly useful when you have multiple servers with different capacities. For example, let's say server A and server B each have 4 GB of RAM and 7,000 CPU units, while server C has 8 GB of RAM and 14,000 CPU units, which is double the capacity of the other servers. Therefore, server C can handle double the load. In this scenario, we assign a weight to each server. Servers A and B are given a weight of 1, and server C is given a weight of 2. So as the requests come in, request 1 goes to server A, request 2 goes to server B, request 3 goes to server C, and request 4 also goes to server C because it has double the weight. Request 5 goes to server A and the cycle repeats itself, ensuring that the server C receives double the requests because it has double the weight. Another interesting approach to static load balancing is source IP hashing. In this method, whenever a request arrives at a load balancer, it extracts the IP address of the client making the request and hashes it. Hashing is a process where an input is converted into a value using a mathematical function. The same input always produces the same output, known as the hash. To learn more about hashing, you can check out my other video dedicated to this topic. If the load balancer receives an IP address for the first time, it creates the hash of the client's IP address and maps it to one of the servers. Let's say, in this case, it's server A. The load balancer keeps a track of this mapping. Now another request comes to the load balancer from a different IP address. It creates a hash of this IP address and maps it to the next server. The next server may be chosen by a round-robin or a weighted round-robin algorithm. In this case, let's say it maps to server B. Now, when a new request from the first IP address is received, the load balancer hashes the IP address again and finds that this hash is already mapped to server A. so it sends this request to server A. Therefore, requests from new IP addresses are distributed to the servers using round-robin or weighted round-robin approach, but the requests from known IP addresses are consistently sent to the same server where previous requests from the same IP were directed. This ensures that the load is well distributed, but the requests from the same client always go to the same server. This approach is particularly useful in stateful applications where sessions are used. For example, if you log in into a stateful application, your login might be handled by server B. With source IP hashing, all the subsequent requests from the same IP will go to server B, which has your session information. If the requests were sent to any other server, you would be asked to log in again, which is not an ideal user experience. This method of session maintenance in a distributed environment is called session affinity or sticky sessions, and source IP hashing helps ensure this. There are also other more advanced ways of ensuring session affinity as well, but this approach is the most basic one. While this technique is effective, it is important to note that it might lead to an uneven load distribution if some clients make more requests than the others. So let's try to summarize the static load balancing approaches that we discussed. So the first one is round-robin, where the requests are distributed in a round-robin fashion. This approach is optimal when all the servers have similar capacities. The next one is weighted round-robin. Weights are assigned to each server based on their capacity. Server with higher weights can handle more requests. This is optimal when servers are of different capacities. Source IP hashing. This method can use any static or dynamic load balancing algorithm, but ensures that the requests from the same IP address go to the same server. It is particularly useful for stateful applications where sticky sessions are required. Now, let's talk about dynamic load balancing. In dynamic load balancing, we take the latest server states into consideration, like how many connections each server has, how busy a server is, server response times, and such. So let's dive into some dynamic load balancing algorithms, starting with the least connections algorithm. So here, the load balancer keeps a track of the number of connections each server has. So when a new request comes in, the load balancer sends this request to the server having the least number of connections. This is useful when all the servers are of similar capacity. The main advantage of this approach is that it ensures that no server is overloaded with requests. And then we have weighted least connections. This approach is quite similar to the least connections approach, but it is useful when there are servers with different capacities. In this approach, each server is assigned a weight based on its capacity. The load balancer keeps a track of each server's weighted connections. So if servers A and B have the same capacity, and if server C has double the capacity, then the weight of servers A and B will be 1, and the weight of server C will be 2. Now, let's say that server A has 10 active connections, server B has 12, and server C has 16. In this case, the load balancer divides the active connections by the server weight. So the weighted ratio of each server becomes 10, 12, and 8. As we can see, server C has the least weighted ratio of the three, meaning it is the least busy in terms of connections. Therefore, the new request will go to server C. Now, if the number of connections were any different, the decision would also change. For example, if server A has 20 active connections, server B has 15, and server C has 50, then the weighted ratios would become 20, 15, and 25. In this case, server B has the least ratio, and the next request would go to server B. Next approach is the least response time. This approach makes use of both least connections and response times of servers into consideration. The algorithm is simple. The load balancer keeps a track of two things. 1. The number of connections each server has, and number 2, average response time of each server. When the request comes in, first the load balancer finds the server with least connections and it sends the request there. If there are multiple servers with the same number of connections, then it chooses the one with the least average response time. For example, if server A has 10 connections, server B has 20, and server C has 5, server C will be chosen because it has the least connections. However, if B and C both have 8 connections each, then the load balancer has to choose among the two. If B has a response time of 80 milliseconds and C has a response time of 100 milliseconds, the load balancer will choose server B. This brings us to the most interesting dynamic load balancing approach, that is, resource-based load balancing. This approach uses metrics of server resources like CPU utilization, memory utilization, disk usage, and such to make its decision. Depending on what our application is designed to do, we can use one or more of these metrics. For most business applications, CPU and memory utilization are enough metrics, but in some cases, some extra metrics might be used. For example, we measure the CPU and memory utilization in terms of percentages. So if we have 3 servers A, B, and C, their metrics could look somewhat like this. The load balancer will keep a real-time track of this information and tries to find the most underutilized server and sends the request there. To find this, a weighted scoring algorithm can be used. For example, if CPU utilization matters more to us, we can assign this metric a weight, for example, 2. And for memory utilization, we can assign a weight of 1. So we can calculate the score of each server by using this formula. So our server scores will look like this. Here we can clearly see that the utilization for server B is the lowest and it stands with a score of 100, which means the load balancer would send the request to this server. This technique is quite solid. It diverts the requests depending on the status of the resources. Even if there are multiple servers with different capacities, this method would work quite well. It is also quite useful in cloud environments where we need autoscaling. A newly spawned server might be underutilized, and this technique can ensure that the new server quickly gets the load. The only drawback to this approach is that the metrics of each server must be very accurate, and there may be an overhead of collecting this data in real time. To summarize the dynamic load balancers, we have the least connections method, which sends the request to the server which has the least connections. Then we have the weighted least connections method, which does the same thing but assigns a weight to the servers according to their capacities. The number of connections are divided by the weight. The next request goes to the lowest weighted ratio. Next we have the least response time, which first finds the server with the least number of connections. If there are multiple, it sends the request to the one with the least average response time. Finally, we have the resource-based load balancing, where each server's metrics are taken into consideration and the most underutilized server gets the request. So that's all, folks. I hope you have a better understanding of how load balancers keep everything running smoothly. Let me know in the comments below which other system design topic would you like to see next. See you in the next video. Bis dann.